I was telling you about the field equation in my last lecture, and I also said that the field equation can be obtained by simple Euler-Lagrangian equations, and I tried to write them out in a tensorial form. That is, one can write it like using tensor notations, and I will try to write them now. So it's the same index there, del I and del I there and del I here in the denominator, minus del L by del of AK, right? It means that we have the action, and we are varying the action, putting this equal to 0. The variation of the action is with respect to the field coordinates. So this thing is being varied with the field coordinates. Now the field coordinates are, of course, AK, or you can write AI. Okay. So when you vary the action with respect to the field coordinates, you get the field equations. And in these field equations, you have to put the expression for the Lagrangian. Now, I call it Lagrangian, but it is basically Lagrangian density. Okay. And how much was it? So last time I told you that the Lagrangian density is given as minus 1 over 16 pi, then Fik minus 1 over C. You can write A, L, J, N. Okay. Now in this is the term which corresponds to the free fields. So we call it the Lagrangian due to fields alone, right? Because the fields can exist independent of any particle, charged particles in it. The second part is, of course, the source term. So if you have the charges and the currents in certain situation, and those charges and currents might create the fields, that is Fik, then you can always write the total Lagrangian, and the total Lagrangian includes these two parts. Okay, and each of them is negative for the same reasons which I explained to you in one of my earlier lectures. So here you have Ji, and because of this you have AI. There should be interaction between the sources and this AI and Ji. There is an interaction between the two, and this interaction between the fields and the charges we had already understood last time. And if you can see those expressions, go back a little and try to find out as to what were these terms for the interaction of AI and Ji. You would find that this term basically comes from the interaction of the charges, that is Q by C, and AI dxi. Okay. Now remember that this was the action for the interaction part, okay, which I discussed last time. So from here, one can easily see that this term is again giving rise to this term in the Lagrangian. Okay, the Lagrangian here is actually due to the interaction of the sources with this charge. Okay, so the charge is interacting with this. That is why these two terms are sitting in the interaction term of the action. And it is the same thing which gives rise to the action for the sources and the fields, right? How do we ensure that it is the same part of interaction which is coming here? In order to do so, we have to understand that the action now should be written as what? L and d4x 1 up over c, right? This is the Lagrangian density. This is okay for the fields and plus the source. Okay, so you can break it into two parts again, and then see, you can write it again. That is minus 1 over 16 pi c and f ik f ik and d4x. This will be the action just due to the fields, and then minus 1 over, we had c there, so it will become now c square, and then you can write a l j l, right, or whatever you like. Okay, so this is what you get in the action. Okay, and so when you concentrate on this particular term and connect it with the earlier interaction term, you compare this, then you can see that for particle, we were talking about interacting part of action as Q by C. This was for interacting Q by C, and then AI and DXI. Okay, so we can go a little further with this and try to show that it is the same term which was appearing on my last slide. So in this slide, we had this second term, and this second term is the same as the term now. You can write it like 1 over c. Just try to open it out and it will come fairly easily. In place of q, you can write rho d3x, and you can open up the next term, that is ai, so you can write it always like this, a0 dx0, okay, plus you will write a1 dx1, a2 dx2, a3 dx3, because I is the dummy index here. So in place of writing 1, 2, and 3, I can simply write a mu and dx mu. With this understanding that this mu goes over 1, 2, and 3. Let us do it a little bit further. We can write it like 1 by c square, and let it be rho c, right? And this is of course d3x, then multiply whatever is inside, so you will have this. So this is, let us say, the first term, plus you will have rho c, and d3x is there, then a mu, and I convert this dx mu into the velocity, that is, I can write dx mu by dt and multiply by dt. right? So since one can write it like this, the advantage is that it can be recognized as the velocity, and then further you can write 1 over c square. Now this rho c is nothing but J0, and it is A0, and d3x and dx naught, the product of these two is the 4 volume. Okay, so you have to multiply the physical 3 volume d3x with cdt, and then you get the 4 volume, and 4 volume is Lorentz invariant quantity. So that is why we respect it so much. Ordinary volume is not Lorentz invariant because that will appear to be different with respect to different moving frames, but d4x will be always the same, and one can check this also. The second part will be what? You have here rho and dx mu by dt, so it is basically rho c d3x, right? Combine this thing and this dt a mu v mu. So this a mu is a1 a2 a3, and v mu is v1 v2 v3. So with this, the first term is there, which is a0, and of course d4x, and minus 1 by c square, the integral sign. So the net result of all this is that you have 1 by c square, and inside you have this a0 j0. Please take this d4x also outside, so you can write a0 z0 plus you can have rho into v mu is actually j mu, so you can write this as a mu and j mu, and take this d4x outside. So this is 1 by c square, and al jl. Can use a dummy index. L goes from 0 to 3, so 0 term is there, and 1 to 3 are sitting in the second term there. So al jl, and then because this is equal to an action, so the action can be written in terms of the Lagrangian densities. So when you write in terms of the Lagrangian densities, the action is L d4x, right? And of course, 1 over c. So if you compare this thing with our expression that we have now got, you can immediately see that this Lagrangian, which was due to interaction only, minus 1 over c, and then al jl. So just extract this quantity, okay? Because you know this relationship that the action has to be this, and this is just the interaction part. So we got the same term which we were using in our Lagrangian for the fields. Okay, so if you go back to my slides and see what kind of Lagrangian we were using. So we were using this part of the Lagrangian here. Okay, that shows the interaction of the sources with the fields, right? And this we have obtained again through the particle interaction term, the exercise which we had done in our last meeting. So what it means is that we have the same term, right? And we can now combine, if we like, we can write down now the total action, charges And when I say charges, it includes currents, charges plus the field. Now how to write it? So let us pick up the first term, minus mc ds, right? So this was the free particle term, which we had earlier used. Then we have the term due to fields, which I just wrote. So because action is equal to 1 over c integration of L Lagrange density, so we will write here an integration of f I k, right, and d4x. All right. And then comes the third term, which is minus 1 by, now it should become c square, because that was 1 by c, and another 1 by c factor has to come from the definition of the action. And it can be now written as ALGL d4x. Okay. So please recognize these terms. The first one is the free particle term, when the particle was free or the particles were free. So when you say particles were free, then you have to basically sum over other particles, right? Let us now put a suffix for the particle number. Let us call it as A and then A here. So you have to sum over A, I mean all the particles, right? And all the particle will have their different word lines. So you should also put BSA, right? This FIK is okay, but particles are playing their role in JL. So you have to make a summation here again, okay? So you can write down the full, the total action about the full system. Okay, so we just saw that this part can also be written as minus Q by C A I dxi. So it's the same term that we were using in our interacting part of the Lagrangian while talking about the particle in the field. We had used this term and we call it interaction term. But now we see that this interaction term is equal to the source term, because both of them are equivalent. So this is the total action. And now the action principle tells us that if you vary this action, you can get the equations of the charged particle, which is the Lorentz force law, or you can also get the field equations, which are the Maxwell's field equations. But the recipe or the technique to obtain them is slightly different. So if you want to obtain the equations of motion of the charged particle, then you have to vary this action with respect to DSA. But if you vary this action with respect to the field coordinate, right, then you get the field equations. And we may have the occasion to refer to this slide again and again. So I told you two ways. Okay, you can vary the action with respect to DSA, which is the word line of the particle. You can vary it with respect to this, and then you get the Lorentz force. Or you can go by varying this action with respect to AIs. So two ways of varying action, Vary it with respect to DSA, you get the Lorentz force. Vary it with respect to AI, and you get the field equations. Okay. So it is nice that जिसे हम हिंदी में कहते हैं कि एक पंथ दो काज ना, ये एक फायदा हुआ, एडवांटेज हुआ हमको कैनोनिकल मेथड से इलेक्ट्रोडायनेमिक्स को पूरी को ऑब्टेन करने का, कि एक हमको टोटल एक्शन पता चल गया और उस टोटल एक्शन से ही हम दोनों चीजें निकाल सकते हैं। हम लॉरेंट फोर्स लॉ भी निकाल सकते हैं और हम फील्ड इक्वेशंस भी ऑब्टेन कर सकते हैं, राइट। तो पिछले लेक्चर में हमने ये ऑलरेडी किया था कि अगर हमको एक्शन मालूम है तो उस एक्शन से हम लॉरेंट फोर्स कैसे निकालेंगे, और वो इक्वेशंस कौन सी थी। वो इक्वेशंस हमको मालूम है, डी बाई डी टी ई माइनस डेल एल बाई डेल आर इज इक्वल टू 0, राइट। वी ऑल नो these equations, और इन्हीं को यूज करके आप ये निकालेंगे, ठीक है। और यहाँ के लिए जो इक्वेशंस हैं, जो फील्ड इक्वेशंस हैं, वो मैंने अभी थोड़ी देर पहले ही लिखी थी, उसको मैं दोबारा यहाँ पे लेट मी राइट। याद रखिए यहाँ पर हमको लैग्रेंजियन डेंसिटी यूज करनी है, और ये आप देखते चलिए कि जब हम फील्ड के लिए इक्वेशन लिखते हैं तो हमको कौन कौन से चेंजेस इंट्रोड्यूस करने पड़ते हैं, राइट। पिछले लेक्चर में मैं आपको ये बता चुका हूं कि हम लोग एल की जगह पर हमने यहाँ लैग्रेंजियन डेंसिटी यूज की है, राइट। सो फ्रॉम एल वी गो टू द लैग्रेंजियन डेंसिटी, और हमको ये भी पता है कि अगर हम इसको मोमेंटम, जनरलाइज मोमेंटम की तरह से आइडेंटिफाई कर सकते हैं, ताकि ये एक जनरलाइज फोर्स बन जाए डी बाई डी टी ऑफ दिस, हालांकि ये विद रिस्पेक्ट टू टाइम है, कोऑर्डिनेट टाइम है। तो इसी प्रकार से हम इसको भी एक जनरलाइज्ड फील्ड मोमेंटम, जिसके अंदर फील्ड हैं प्लस पार्टिकल्स भी हैं, सोर्सेस भी हैं, उनके हम कॉम्बिनेशन के जनरलाइज्ड मोमेंटम के रूप में इस वाले टर्म को यूज कर सकते हैं, ठीक है। बोल सकते हैं कि ये भी एक जनरलाइज्ड मोमेंटम है। कुछ रेपिटेशन भी इसमें हो गया, बट लास्ट टाइम I was trying to find the first term and of course the second term. अगर आपने ये क्वेश्चन नहीं किया है, so then I would advise you to do it now. ये निकालिए पहला टर्म और दूसरा टर्म कैलकुलेट करिए, ठीक है। और जैसे ही आप ये टर्म्स कैलकुलेट करेंगे तो आपको मैक्सवेल की फील्ड इक्वेशंस मालूम हो जाएंगी। So Aditya Mishra is asking, so what is the meaning, physical meaning of the symbol in the total action? Actually symbol जो यूज किया है वो हमने A यूज किया है यहाँ पर, तो टोटल एक्शन के लिए एक A सिंबल यहाँ पे यूज किया गया है, राइट। और A सिंबल यूज करने का कोई अलग कारण नहीं है, you had to use some kind of a symbol which is distinct from the potential.
Hello.
Yeah. Yes, please.
Sir, he is asking what's the significance of negative sign in action.
So I had already told this, negative sign of action is necessary in order to make it minimum. And I, even when talking about the free particle, I had told that this negative sign ensures that the action becomes minimum, or rather extremum, and it does happen, or it can happen for a particular case when the particle is at rest. So in the rest frame of the particle, you always have this quantity going to be minimum. If there is no negative sign, then unfortunately you will not be able to minimize this quantity or extremize this quantity. And that is the crux of finding action, because action is something which can be minimized. So you have to explore some quantity which can be minimized or extremized. Okay. So yes, this minus sign helps you in discovering a quantity that can be extremized. And in fact, nature tells you, nature is asking you for a favor that, okay, go and find out some kind of a quantity which can be extremized, right? And
Right,
then
sir.
you come back with the answer that, okay, you have the minus sign and then this quantity can be extremized. Otherwise, it cannot be.
Okay, sir. Thank you, sir.
Sir,
Yeah, go ahead. Go ahead.
sir, would you explain why we use summation sign in third term of total action again?
You mean on the slide which I have now on my screen?
Yes, sir. Yes, sir. Yes, sir. Third term summation.
So the third term minus 1 by c square. So you are asking me why I am adding this. Is it your question?
No,
or
sir.
what?
No, sir. I am asking it why we use summation sign here with respect to what?
He's
Okay,
talking
okay.
about sigma, sir.
Okay. So this sigma actually takes care of the fact that you could have a number of charged particles moving around. Okay, so they all form J, and in that case you have to designate this J with the current. I mean the currents for with the suitably you have to fix up this J with the moving particles or moving charges. So you can call here JA, right? Now A is not a tensorial index, it is just to label that particle. So JA, and you have to sum over A as well here also, right? So please try to write this expression on your own in a more elegant and clear manner, right? So now this expression becomes minus 1 by c square, and the summation over A means the level of the particle. So you have to do it independently for all the particles. Then you have to put them here. So ALJL for one particle plus ALJL for another particle, then ALJL for third particle, and so on and so forth. So you have to make a summation because you have a collection of the charge, right? So collection of the charges, I already said it is charges here, right, in the title. So since you have many charges, so look carefully the first term also. The first term also included this summation. Now this summation is again over individual charges. So MA means the mass of the particle, which is labeled as A, and DSA where it is going, the word line of that particle, and you have to do the summation over all such particles, right? Also, if you can see that this expression is basically it can be written in a more simple way. That is, you can write it as minus mc square, and this was also the expression that I was using, and then square root of 1 minus v square by c square. I told you this is the Lagrangian, right? And then if it is the Lagrangian, then here you have to introduce dt, right, which is the coordinate time, and then you have to do the integration. You can write this thing also. Now for labeling the particle, again you have to take one particle, let us say MA, so fix up this, put the suffix for A, and it can have a velocity A, so put up another suffix there as A, and then take the summation again of the entire expression over A. So this integration is being done because you have to include so many particles. Now at the same time, when I was writing this equivalence, in the last expression below in the red loop, you have to, here also you have to do the summation, right, over A, right? And this will become now QA, that is the charge A. So this makes a complete story that you can have several charges and all the charges will be contributing to the interaction with the source. Is it fine? Any other question? I hope it answers your query.
Sir, please repeat again the physical significance of second part. 1 upon 16 pi c phi k d4s.
Right. So this is the free field term. It is coming from the fields, directly from the fields. So if you don't want to consider anything else but the fields alone, then you will have FIK. So last time I told you that what are the criteria which necessitate you or which are required to write down this term. That is, you have to find out some expression which is quadratic. Do you remember that? Quadratic in the generalized velocities. And this FIK is quadratic. FIK is the quadratic term in the generalized velocity. Apart from being so, it is also a Lorentz scalar quantity which you need. So you need certain conditions for the action to satisfy, and these conditions being met. Action overall should be Lorentz scalar. So each of these terms, the three terms are there, but each of these three terms is a Lorentz scalar quantity. Okay. So when
Yes, sir.
deciding, yes. So is it again someone asking this statement true that if the contravariant indices are true for left-handed frame, then the covariant indices do the same thing for the right-handed frame? Is very vague statement. And the contravariant and the covariant indices or the four vectors are defined in mutually dual space-time, and they have nothing to do with the choice of your handed system, whether it is right-handed or a left-handed system. Okay. So in a special relativity, we can always convert a contravariant index to the covariant index by using that ladder which I had told you as GIK. So you can always like this. Now, why do we even need the dual tensor for EM field? I'm asking because we already have elements of E and B in. Now, we already have the elements, yes, and it's true that this F star IK will not do anything new for you, and this you already saw in writing down the homogeneous set of equations. There you can write down the equations using them, but it's a matter of convenience, especially when you go inside the matter and then you write certain field invariants, then it becomes easier to use that dual field strength tensor there. For example, in the problems which I gave you, like G star IK, then I use their F star IK as well. So these give you the definitions for the polarization tensor in a general way inside the matter. But of course, the information carried in the dual tensor is the same as the information carried in its counterpart. Yes. Any other question? Okay. So what I was then telling you is that there are two ways of varying the action, and once you write the whole action, then you can go either way. In the earlier approach which you have learned in your last semester, the field equations were given separately, and the Lorentz force was written down separately as if there were no connection. But now you know that both of them are coming from the same A, right? So this A is the key quantity that we are after, and we take this question again of finding out this term, and you have to find the first term and then you have to find the second term in this. It is fairly easy because L which you use there is it contains the field terms as well as the source terms, so it will be a combination of the two, and then you can find it out. And I had told you that in order to do this problem, you must first find this, right? Then you can also try to find out FLM this del IAK could be understood as the generalized velocities, and this you should try to find out. Then you should also try to calculate the second term of the Euler-Lagrangian equations for the fields. So that was it was what? Del of AI, right? Now I, right? Now don't worry if you use I, K, M or L or any kind of indices. I have repeatedly told you that these indices are based on our choice, and you should feel comfortable about using any kind of index, any kind of symbol for the index as you please. But ensure that your equation should be tensorially correct equation. The expression should be tensorially correct. That means you have to see the indices on the free indices on the left hand side of an equation should be matching with the free indices of the right hand side of the equation. You have to also take care of choosing what are the dummy indices in the expression and be very careful about it. Okay, so use this L and try to do this problem. And then I had told you that once you can do these two terms of the Lagrangian equation, that is 1 plus 2 is equal to 0, right? If you can find out the first term and the second term, then from there you can establish that del I f I k is equal to 4 pi by c jk. Okay, so these are easily identified as the so-called Maxwell's field equations. And as a next step, if you take the derivatives further, del I f I k, you do del k, right? And also del k here. Okay. And can you show that this quantity, this answer should be 0? Now, if it can be 0, then this would establish that this thing is 0 and this thing is nothing but the statement for the conservation of the charge. So it is like del k jk is equal to 0. So we have obtained the conservation of charge from action principle. Okay, and this is again another success of the action principle, that it tells you so many things. So this A total tells you how particles move, right? It also tells you how the fields behave. It also tells you the conservation of charge, right? So many things are ascertained or fixed up once you know the total action. Also remember that this action is only true for flat space-time, that is spatial relativity. It is not true in the presence of gravitation, right? So for gravitation, you have to make some changes. I will not go into that. So if you put your action in gravitational field, you get to a very beautiful idea, what is called minimal coupling, right? Although one can see that Fik remains the same. So you have Fik, it remains the same in presence of gravity. So it does not change in presence of gravity.